and welcome to T Academy. In today's lecture, we'll be talking about exponential signals. An exponential signal can be written as C e to the power beta times t, where C can be real or imaginary, and beta can also be real or imaginary. For today's lecture, we'll assume that C is real and we'll be looking at both cases of beta, where beta is given by sigma plus j omega. We'll be looking at both the cases where beta is purely real or when it is purely imaginary. So the second case where beta is purely imaginary. So we can write that signal as e to the power j omega t. So before we proceed further, I would like here to introduce the concept of a period. Let's say we have a signal like this, a triangular signal which repeats after a certain time t. So this is the signal x of t versus t, and as you can see from this signal, the shape of x of t repeats after t and also after 2t and so on. So after nt, x of t repeats itself. So x of t is periodic if x of t is equal to x of t plus n times capital T. So capital T here is the period. So after an integral multiple of t, if the signal is repeating itself, then we call that signal as periodic. And when n is equal to 1, we are left with x of t is equal to x of t plus t. So the smallest period is called as the fundamental. The smallest period after which the signal starts repeating itself is called the fundamental period. So if we want to check the periodicity of our exponential signal, we can write e to the power j omega t is equal to e to the power j omega t plus t, capital T. So from this explanation, we know that e to the power j omega t would be periodic if it equals to e to the power j omega t plus a certain period, capital T. So if we simplify this further, we can write e to the power j omega t is equal to e to the power j omega t times e to the power j omega capital T. So this cancel out and we are left with e to the power j omega t equal to 1. From Euler's identity, we know that e to the power j omega t can be written as cosine of omega t plus j times sine of omega t. So you can check my lecture on Euler's identity where I derived this expression from the Taylor series expansion. Euler's relation is known as the joule of mathematics, and we will use that a lot in this lecture series on signals and systems. So replacing e to the power j omega t with 1, we are interested in finding out when does the argument of cosine omega t plus j sine omega t equal to 1. So a cosine signal, you all know it starts at 1, goes to 0 at pi by 2, and then it goes like this. At 0 it is equal to 1, pi by 2 it is equal to 0, at pi it is equal to minus 1, at 3 pi by 2 it is equal to 0, and at 2 pi it equals to 1. So this is the graph of a cosine function. On the other hand, a sine function starts at 0, at pi by 2 it is equal to 1, at pi it becomes 0, at 3 pi by 2 it is equal to minus 1, and at 2 pi it is 0. Since a sinusoidal function is also a periodic signal, we can write that cosine omega t is equal to 1 when omega t is equal to 2 pi or an integral multiple of 2 pi, since it will also be 1 at 4 pi, 6 pi, and so on. On the other hand, sine omega t is equal to 0 when omega t is equal to an integral multiple of 2 pi. And from here we find omega as 2 pi n over t, and the fundamental frequency omega 0 is when n is equal to 1. The fundamental frequency is given by 2 pi by t 0. Now let's look at this expression in some detail. Omega naught is the angular frequency in radians per second. T naught is the fundamental period, and f given by omega naught by 2 pi is the frequency in hertz. So let's say I have a sinusoidal signal like this. We have already seen that a period, the fundamental period, is the time after which the signal starts repeating itself. So this is, say, x of t versus t, and after the fundamental period the signal repeats itself. From here we see that the time period t naught is given by 1 by f. So for the first case, let's assume that the period is equal to 1 second, and thus the frequency is equal to 1 hertz. So let's say this is a 1 hertz signal. Now if I reduce the time period to half, let's say 0.5 second, then this signal would start repeating after 0.5 second instead of a second. So let's plot it. So after half a second, which is this, the signal will repeat itself. So the new signal will complete one cycle in half a second, and then it will repeat itself like this. So since t naught is reduced, the frequency will increase, and frequency in this case will become 2 hertz. So this blue one is a 2 hertz signal, and you can see that its oscillations per second have increased. So frequency can be interpreted as oscillations per second, and a high frequency signal has higher oscillations than a low frequency signal. So we'll continue our discussion on exponential signals and periodic signals because both are closely related by the Euler's relation in a future video. So if you like my channel, then please do subscribe. I'll see you in another lecture. Thank you.